Welcome everyone to this PUM solar course. My name is Wijdeveld and I will be your teacher for this lesson. But let's tell me first something about myself. As said, my name is Wijdeveld. I'm 60 years old, living in the Netherlands, and I have my education as a bachelor degree in electrical engineering and a master's in renewable energy. I've worked with different international companies like Philips, Honeywell, SolarEdge, and Spirotech. So I hope you will enjoy this lesson. What will you learn in this lecture? I will tell you about grid-connected solar systems. And I will divide it between residential solar systems and commercial solar systems. And very related to grid-connected solar systems is the solar grid inverters. And also I will tell you a little bit about monitoring. That's also in relation to the grid inverters. But let's start about the grid-connected solar systems. A grid-connected solar system is, as what it already said, it's connected to the local electricity grid. It's by far the most common and widely used solar systems. You see them everywhere, and it's very often used also for residential houses, for large commercial and very big utility scale systems. So it is connected to the grid, and normally there are no batteries involved. Of course, you can connect batteries with it, and it is no off-grid system, but it is possible to have batteries as backup. And any excess solar power is exported to the local electricity grid. I will come back to that in detail. We have different types of solar systems. We have the off-grid solar system, that is a system which is not connected to the local grid. In another lecture, you will learn everything about the off-grid solar systems. And the off-grid solar system, you have also a battery is involved in that. I will tell you about the on-grid solar systems, so the systems which is connected to the local grid. And then we have also the hybrid solar system, which is basically a combination between off-grid solar system and an on-grid solar system. In another lecture, you will learn everything about the hybrid solar system. But let's focus on the on-grid solar system. We have them for residential houses. You see them on the roof, and normally the capacities are, say, till 10 kilowatts. So something about 35 solar modules. And people have this on the room mainly to cover their own electricity use. So all the electricity what is used in the house is produced by the solar system on the roof. It is a quite easy system, straightforward. You have normally one inverter, and it can be either a one-phase solar inverter for small systems or a three-phase inverter for bigger systems, but bigger is, say, about 10 kilowatts. Normally you don't need any permits to put this on the roof. As said before, sometimes you can have it with a battery for backup, and it's financed by the homeowner. So the owner from the house will also buy this solar system. If you go to the commercial solar systems, this is a little bit bigger. And normally you see them on factory roofs or roofs on schools or the bigger buildings. The capacity goes to about 1 megawatt, and 1 megawatt represents about 3,500 modules. It's also mainly to cover the own electricity use of that building, of that specific building. Depends, of course, it's a factory with heavy machines. You never will cover all electricity, but at least some of them will be powered by solar energy. It is a little bit more difficult to install because you have more inverters, you have more three-phase inverters, you have more wiring, you have to take care about safety issues, and so on. And you need agreements with the network provider for connection. You can understand if it is in full production, it produces quite high amps and a lot of power. And the network must be able to handle these powers if you export it back into the grid. You need an agreement with your energy supplier for the energy deliveries and pricing. So you have to make an agreement with your energy supplier about the price if you export the energy back into the grid. And the financing is either done by the tenant of the building or the owner of the building. Now you will see the bigger solar systems, the solar plants. It's called also the utility scale solar plants. Those are very, very large fields of solar panels, up to more than 2,000 megawatt, 7 million solar modules. These are all, of course, on ground and mainly in desert areas where there is enough sun and enough space. These plants are specially designed for the electricity, producing electricity for the utility grid to power a city or some different villages. It is very specialized installation work. You have central high voltage inverters, and it's designed together with the network providers for connection and the energy transport, because you can understand you need special wiring, you need high voltage wiring going to there and transporting the solar energy to a certain location, for example, a grid, and connect it over there. Also in cooperation with the energy supplier for the deliveries. Of course, someone who is investing in this wants to have a revenue and wants to have money from the energy that he produces. So with the negotiation of the energy supplier, he agrees a price against which he can sell the electricity. And it is financed together with investment companies. There are special companies, die say, oh, that's a good revenue, it has a nice return of investment, I want to invest in this solar plant. But let's focus more to the smaller systems, to the residential solar systems. Here you see a schematic diagram of a common solar system. We see the PV modules on the roof, and this converts the sunlight into electrical DC power. In the first lesson, you've learned that out of a solar panel, or out of a solar cell, there is DC current comes out there. The DC strings are connected with the PV modules, and the strings are connected together. These strings, and that can be one string or two strings, goes into the inverter. The inverter converts the DC power from the PV modules into AC power. The inverter is connected to an EC breaker panel for safe disconnection. So if something wrong with the inverter or with the panels, you can switch off the inverter at the EC breaker panel. But the EC breaker panel arranges also the energy distribution. So from the solar panels, the energy flows through the inverter into the EC breaker panel, and then the energy goes either going into your house to supply your household equipment from solar energy, so all the lamps, the refrigerator, and so on, or the energy goes back into the utility grid. Or when the sun is not shining, the AC breaker panel makes that the energy which comes from the grid goes into your house. This is a diagram from the grid connected solar system. It exists actually out of 3 blocks. One is the PV array. Those are the solar modules connected in series as a string, and some strings are connected in parallel. The strings are connected to the grid inverter, and the grid inverter is a part of the balance of system. And the balance of system is the grid inverter and the distribution panel, or the AC panel, which I discussed in the previous slide. And then it goes into the loads from your house. Let's assume a solar system, and a solar system produces the total home energy, what you need in your house. For example, the solar panel produces 4,000 watt solar energy of power. It goes into the inverter, and your house needs 4,000 watts as consumption. So all the energy, all the solar energy goes to your house. There is no need for electricity from the local grid, so the energy meters measured nothing. Let's assume that there is a cloudy day and the solar panels produces only 2,000 watt. The 2,000 watt goes into the inverter transfers the 2,000 watt to your house, but your house needs 2,000 watt as power, as consumption for powering the equipment in your house. Then 2,000 watt will be imported from the grid to add to the solar energy to have the 4,000 watt, and the energy meter counts up. Let's assume that there is no sunshine, for example at night. Your house needs 4,000 watt because the lamps are burning and the fridge is running and whatever. There is no solar energy, so all the energy comes from the local grid, and the energy meter is counting up. Let's assume that on daytime, the solar panel produces 4,000 watt, but your house needs only 2,000 watt. You switched off some equipment, some lights, and so on. So you need only 2,000 watt in your house. The solar system produces 4,000 watt. So 2,000 watt will be exported to the local grid, and the energy meter is counting down. We mentioned a couple of times the local grid. And the local grid is actually a very complicated network. And in this network, a lot of things are connected to this grid. We see power plants, we see houses, we see electrical cars, we see industrial loads, we see even hydro plants, batteries for storage. And in this network, all the energy flows to left, to right, to everywhere. So you can understand that it's very difficult to manage. And to manage this very well, it's called, in a grid, it's called a smart grid. We have the traditional grid, which comes from a power plant, and with a thick cable, the power which is produced by the power plant will be distributed to the houses, and the further away, the thinner the cable it becomes. But now these days, with solar panels everywhere, the energy comes from all directions into the grid. And sometimes this causes grid problems, because the original grid is not designed for having this this energy flow. So there you always have to check with your network provider for, can I connect my solar system to the grid? Is that possible? Is the grid designed, or is it possible to have my solar system export energy into the grid? Connecting to the local grid. So as said, check your local network provider if you can connect your solar system to the local grid. Check your network provider if you can export excess energy into the local grid. So that means if you can export the energy, if you produce more energy than you consume by yourself, can you export the energy what you've produced more, or what you basically not directly need, into the grid? So for most small systems, this process of grid connection is streamlined. Check your export limit. Sometimes the network providers have limits how much you can export into your grid, and for which amount you can get your feed-in tariff. I will come back to that later as well, the feed-in tariff. So these limits should be considered when you're sizing your solar system. So for solar systems up to 5 kilowatt, you may have to negotiate with your network provider for grid connection. Reasons for no grid connection is, as you saw in the previous slide, the network is not designed for bidirectional energy transport. And bidirectional means both sizes. There are already many solar systems connected to the grid. So on days when there is a lot of sunshine and hardly any demand, the grid can have problems. They're receiving so much energy that they don't know what to do with that energy. And sometimes the network provider says no, we have already too many solar systems on our grid, it is not possible. So check your network provider. Also, a reason for no grid connection is the cable size is not sufficient. As explained before, the current networks are designed from an energy plant, a power plant with a thick cable, which the cable will be thinner along the line. And if you're at the end of the line and you feed in your solar energy, that can cause problems because the cable sizes are not big enough. The tariff feed-in and net metering. You can actually see the grid as an energy storage. How can you see that? How can you say the grid, you can see the grid as an energy storage. So if you feed in when there is extra solar energy at daytime, and you get it back, for example, at night, when you don't produce solar energy. And sometimes against different rates. So you're producing energy, you bring it into the grid, and at another time you import it back from the grid. We have a feed-in tariff possibility, paying and purchasing. If your network provider says, no, I only work with feed-in tariffs, that means you have to install 2 unidirectional meters. That's a meters that counts only in one direction. So one meter measures the energy imported from the grid, for example, at night. And the other meter measures the excess solar energy, which is exported to the grid. So you pay the retail rate for the electricity you import from the grid, and the energy provider buys the extra solar energy at a wholesale price. And often these are different rates. Yeah, you have to pay normally more if you import the energy, and if you export it, you get normally a lower price. Net metering, also called energy equalization. You have a single bidirectional energy meter. And a bidirectional means it measures both sides. Yeah, it measures that energy flows into the grid, and it measures as well that energy comes out of the grid. So it measures up and it measures down. And yeah, so the energy you import from the grid, it counts up. So we have to pay for the energy. And when you have enough energy, excess energy, solar energy, you export to the grid. And the meter, the same meter, counts down. The energy bill over time, for a month or a year, then every imported energy imported from the grid and the solar energy exported from the grid are settled, are equalized. So that's a benefit, because there is no difference between a wholesale rate or a retail rate, because it will not measure it. And this is the way you can see the grid as the energy storage. Yeah, you bring it in and out, and it will and the price will be equalized. So when you consume more energy than produced over time, you will pay the retail price for that extra energy. And when you produce more energy than you consumed, so when you export energy to the grid, you get a wholesale price for the extra solar electricity. But that's also over a certain time, over a month or a year. And in between, you have very often that you import energy from the grid and you export it, and that will be equalized. Large solar systems, or also called commercial systems. The setup is basically the same as for a residential system. We have the solar panels, we have the inverter, we have the switchboard, we have the meter, and we have the grid. Nothing different, only the sizes are different. So we have more modules in a string, and the amount of solar modules in a string depends on the solar module power and the inverter string voltage. So you cannot connect endless solar modules in series, because as you learned in the first lesson, the voltage will count it up if you connect modules in series, and an inverter can handle a certain input voltage. The economy of scale gives also a great return on investment. Lower investment costs per produced kilowatt hour because of the scale. You buy more panels at once. You need to have also more mounting devices. You need more cables, and if you buy more panels, you can negotiate a higher discount rate. Same for cables and so on. It increases as well your property value. So you put something on the roof which is valuable, so the whole setup or the whole building will be more valuable. It's technically more complicated. You have connected to a three-phase grid. You have to deal with higher voltages, higher current, more wiring, multiple three-phase inverters, and there are also safety issues you have to take care of. Again, you need to have agreements with the energy supplier about the price. You have to agreements with the network provider about the connection. And it needs carefully financing to get a high return of investment. But as well, and it is very often used now, it improves a company green image. They can say from, hey, we run on solar energy, we take care about our environmental, and we not take the energy from an example, a coal power station. Solar grid inverters. There are different types of solar inverters. But an inverter converts direct current from the solar modules into alternating current. So the type and the power rating depends on the number and power of the PV modules. The input voltage up to 1000 volt DC so PV modules in series. You have an output, you have which is connected to the grid for one phase, or three phase. The inverters have an efficiency for higher than 95%. And the lifetime of an inverter is 10 to 15 years. So we know that a solar module has a lifetime from about 25 years. So in the lifetime of a solar system, you have to replace the solar inverter one time. You have to take that into account when you make a calculation about the costs over the 25 years. The inverter deactivates at night and starts automatically when the monitoring in the morning when the sun comes up. And it has special functions like the maximum power point tracking and monitoring. We have one-phase string inverters, we have micro-inverters, we have three-phase string inverters, then inverters with optimizers, and we have high-power central inverters. I will come back to that later for a little bit more in detail. The inverter must be designed to synchronize its voltage, waveform and frequency with the local grid to ensure the correct direction of the power flow. That's the main function of the inverter. The function is to, of course, to convert DC to AC power, but if it has AC power, it must be conform the regulations of the local network company. Also, an important feature is islanding. When an inverter or when a PV system continues to power the grid, so exporting solar energy into the grid, even when the local grid is down, if there's a blackout, there can be safety issues. Because the utility workers we switch the utility grid off, so we can work safe on the network. But if a solar system is still working and still powering the grid from the solar, then it creates a dangerous work, because the utilities workers think from there is no energy on, there is no power on the grid, no voltage, but the solar system makes that there is power on the grid. So the inverter must detect a grid failure and then immediately switch off. That's called anti-islanding. The technology from an inverter. So the DC voltage will be changed into a sine wave, and that goes above and below 0 volt. The easiest way to do this is to make the voltage trades up and down, creating a blocky signal. That's called a modified sine wave. You see it in the graph underneath in the orange curve. It's not a nice, it's a very blocky, rough sine wave. And a more advanced sine wave, it creates multiple steps and trying to come as close as possible to the smooth sine wave. That's called a pure sine wave inverter. It's here shown as the blue curve below. So the modified sine wave inverter is just for simple systems. It's also cheaper, but it causes also many harmonic distortion. You can hear that also as a noise. The motors will run hotter. Yeah, they're less efficient. They're using up more energy. So a pure sine wave inverters are preferred. The maximum power point. We've covered this topic also in the first lecture. So I will repeat it a little bit, but not in detail. A solar cell can give only full voltage and full current, or he cannot give the full voltage and full current at the same time. So there is a point at solar cell where it creates a maximum power. And the maximum power is reached at a certain current, at a certain voltage. And that's called the maximum power point. But this maximum power point changes constantly. And that depends on the radiation which strikes on the solar panel and also on the temperature. So the maximum power point is constantly changing. How can we make that the solar system works constantly at the maximum power point to get or to generate the most power all the time? There we have an MPP tracker. And an MPP tracker makes an inverter from an inverter makes that the solar module works at the maximum power point. An MPP tracker is basically a high frequency DC-DC converters which set a working voltage, and the power will be measured. A special algorithm changes this working voltage. So it moves the working voltage a little bit up, calculates, measures the current and calculates the power. If it is a little bit higher, he knows from, oh, I'm in the right direction. I increase the working voltage a little bit more, measures the current again, calculates the power, and he said, oh, this is also a little bit higher. So, and the next step, when the next step is lower, he calculates that the power is lower. He knows, oh, I'm now too far, I'm going a step back. And that will be done in a very high frequency. So the MPP tracker forces the working voltage to set at its maximum power point. So the MPP tracker makes as working voltage the maximum power point voltage. Modules in a string. Only PV modules from the same type can be placed in the same string. And only PV modules with the same orientation or the same angle on the roof can be placed in the same string. So strings with different module types, orientations or angles, they have different maximum power points and cannot be combined, because the maximum power point trackers calculates then an average maximum power point, which never has the optimum from all the individual solar modules. So some inverters have multiple inputs and MPP trackers for strings with different module orientations or angles. They have 1, they have 2 or 3 MPP trackers where you can connect strings with all the same orientation panels, or another string with the same angle. You see underneath a picture from, let's say, the right picture, you see on 2 different shapes from the roof, you see the solar panels. So in this case, I would advise to make 2 strings, one with the panels on the left side from the roof, and another string from panels on the right side from the roof, which is different angles and different orientations. And put these strings all in a separate input from the inverter with the input with its own MPP tracker. So in relation to this, let's have a closer look to the power losses from PV modules in a string. In the left diagram, you see 3 panels connected in series in one string. And we've learned that solar panels connected in series, you have to count up the voltage, and the amp, the current, stays the same over the entire string. So in this example, we see 3 solar modules, each have 6 volt, so 3 times 6 volt makes 18 volt. And the current stays the same over the entire string with this 3 amps. So the total output of this string will be 54 watt. On the right side, we see that one panel is exposed to clouds. although they have still 6 volt, the current drops till 1 amps because it cannot produce enough current. So in this case, the 3 panels modules connected in series is 3 times 6 volt, is still 18 volt, but the current is 1 amp because the weakest module determines the output current. And in this case, we see an output power from this string is 18 watt. So preferred, all solar modules in a string produces the same power. However, this is not always possible, and the weakest solar module determines the total output of the string. If we have a closer look, the reason why we have different output powers. It is because some of the modules can expose to soiling, leaves, dirt, shading, work droppings, which all contributes to the mismatch between the modules in a string. A module can even degrade up to 20% over 20 years. And each module ages at a different rate, causing aging mismatch between the modules. So one underperforming module reduces the performance of an entire string. String inverters. This is a centralized string inverter. We have, it goes up from 2 kilowatt to 150 kilowatts. We have the output for low voltage grid, that's called 230 volts or 400 volts. And that can be 1 phase or 3 phase for all kinds of applications, residential, commercial, and so on. And the number of modules determines the inverter power. And the number of modules in a string determines also the inverter DC input voltage. In a string, the underperforming PV modules, if one PV module produces less than the other in a string, it will influence the performance of the whole entire string. So if you have a string from 5 solar panels and one is broken down, then you will not have any energy because the PV module which is broken will block the energy flow of the solar energy flow. Or a module works only for 50%. You will see that only 50% of that PV module will go through the string. A string inverter can have, as said, 1 or more inputs for power trackers. It's the most reliable and inverter solution, and also the cheapest inverter solution. Solar inverters with
one question, please. It means also that if one module is in the shade in a string, then also the whole string is regarded as being in the shade.
Right, right.
Okay, that's very good to know, yes, because then you have to decide how to configure your strings, isn't it?
That's right. You always have to care that all the panels in a string are free from shade or from trees or from a building, shade from a building. So if one is exposed to shade, that will influence the one panel, will influence all the other panels in the string because they're all connected in series.
Okay, yes, thank you.
Solar inverter with optimizers. It's called also the module level power electronics system. Very mouthful, but okay. It means that every panel has its own optimizer or his own MPP tracker. So we just said if one panel is in the shade from the string and the other not, then with a string inverter you have a problem. Then the solar module which is exposed to the shade, it will define the output current from the whole string. But if you use optimizer, then if one solar module is in shade, then it's a pity, produces less energy, but all the others in the same string produces, and they're not in the shade, they're producing full power. And in this way, you produces more power in the string. But so an optimizer costs, of course, also some money. And it's also do I want to use this? Yes or no? It's also you have more components, and the installation costs are also higher. But the benefits is, of course, if you have one panel not working well in the string, or with shade, or with dirt, or with you have another type, with optimizers, no problem, because it will not influence the output of the string. We have also solar microinverters. This is basically a small inverter for each panel. Each solar panel has its own inverter. That means you don't need a separate central inverter. So out of the solar panel, and if you connect a microinverter to it, the output is directly AC power. So you have AC power directly on the roof. Each PV module can be monitored, and each PV module produces maximum power, independent from the others. It's a higher initial cost, but it is also a higher failure rate, because you have all electronica on the roof at a solar module. And we know sometimes it can be very hot on the roof. And in these microinverters are also electronics. And of course, it's designed to stand this heat, but still there's a chance of a high failure. But it has also its benefits, this microinverters. And then we have the high power central inverters for the solar plants. Yeah, these are for the large systems. We have the central inverters up to 1 megawatt. These are high power. We have inverters for low voltage grid and inverters for high voltage grids. Higher installation and wiring costs, but you have only one inverter instead of multiple inverters. So you have less component connections. You have a good reliability of the system. Inverter selection. Which type of inverter should I select? So nearly all solar inverter companies has design programs for the inverter selection. And also the yield calculation, the cable diameters, a string configuration. So all the main inverter companies has this program, and you can use them for free from the internet. But the inverter power must meet the local of the total PV system power. And an inverter works most efficient as its maximum power. Let's see to the two different possibilities. Inverter oversizing. It's called also a low DC to AC ratio. So let's assume you have an inverter from 4 kilowatt, which is higher than the total system power, which is, for example, 3.5 kilowatt. And in the graph on the right is shown by the purple line. So the system produces the total maximum system power, no problem. But it is less efficient because it doesn't work as its maximum power. And it is a relatively expensive inverter because you have an inverter power which is higher than the system. And so you have actually a more powerful inverter, which is not necessary for the total system power. You can have also an inverter undersizing, so a high DC to AC ratio, which is shown by the green line. So let's assume we have, again, the 4 kilowatt inverter power. And the total system power is now, the solar system power is 4.5 kilowatt. If you follow the line, then there is a chance of clipping, because the total system can produce more power as the inverter can handle. And then the inverter will say, stop, I can work only till 4 kilowatt, and everything above 4 kilowatts is lost. You see that also the area and the energy is lost due to inverter clipping. But you have more energy in the early morning or late evenings or at cloudy days, because the total system power is higher. And for cloudy days or evenings, it doesn't matter. It will never reach the 4 kilowatt clipping area. This system works often with full power, so you have a higher efficiency. But because it works at full power, and it will also, because it becomes hotter, also the lifetime will be a little bit less. So you always have to find the right ratio between the extra produced energy and the loss due to clipping. It's a cheap inverter in relation to the total system power, because you have an inverter which has less power than the total system. But it doesn't mean that you cannot use this. So grid connection, solar system sizing. How large must the solar system be? So check if you can receive your money back when you export solar energy into the grid, because you want to earn money on it. If you export your energy, you will not. That energy is lost, and you have invested in a system, and you cannot get the revenues if you export it to the grid. So you have to check that. Check if your energy meter is counting up and down. Define the power that you need in your home, and at least maximize your self-consumption. Like in the previous slide in the beginning, I showed 4,000 watt. Install as many PV modules as possible and do it safe. Yeah? To fulfill the high level of self-consumption, or as much as you have space on your roof or in the field, or as much as your budget will allow. So for example, a 4 watt peak system, you have, for a 4 watt peak system, you have about 13 PV modules from 310 watt peaks, which gives 4,030 watt. So check the yearly possible solar radiation, depending on the position of the PV modules, and you can make a calculation of the yield. And define your inverter. So a rule of thumb is, if you have a system power from 430 watt peak, so you have 13 PV modules from 310 watt peak, take 0.85 and calculate that and multiply that with the system power. You get 3,425 watt. And of course, you can never have an inverter from 3,425 watts. So select the nearest above inverter power. And the next will be probably an 3,500 watt or 3,600 watt inverter. So take that as your inverter power, which is still lower than the total system power from 4,300, but you have at least a good inverter rate. Solar monitoring. This is a dashboard from a monitoring which you can see, which you can have on your mobile phone or on your PC or on your tablet. The inverter companies offers monitoring software. You have to register your solar system, and you get connection to the website from the inverter company, and you have, of course, to connect your inverter to the internet. And everything what happens in the inverter will be the data will be transferred to the website from the inverter company, and there you can see what's happening with your solar system. You can see the production and consumption of your solar energy. You can see the power flow between the arrays, the batteries, the grid, the house loads, real-time system data. And you can even detect if there are problems with the modules. And you can see also the historical data. If I go back, one slide back, you see here on the left top side, the system data. You can see what is your system, what have I produced today? What is the date of installation? What is the installed power? What have I produced up till now? In the middle top image is the performance. What is he doing right now? What is my average in February? On the right top, you see how much CO2 you saved already, how many trees you saved, how many washings you can do. And on the big chart below, you see the energy production from every day of the month. You see the first is the first day till 31st. And here you can see in a nice graph which day was very sunny and which day was not sunny. And which day produced a lot of energy and on which day I hardly produced any solar energy. That's what we can do with the solar monitoring. In the middle graph, you see an idle production. You see no shade or whatever. So it's a day graph. From the morning, it starts at around 7 o'clock, and around 4 o'clock, you see the highest production, about 7 kilowatt. And in the afternoon, you see it's going down. And at 7 o'clock at night, the inverter will switch off. That's a very nice curve from full a day without any clouds. On the right, you see the graph when there is clouds. You see there are times, for example, between 12 and 1 o'clock. There was heavy clouds. There was no sunshine or hardly or not much sun striking on the solar panels. And the solar panels were not producing at that specific time many energy. That we all can see with the solar monitoring. So grid-connected solar systems, the advantages. You have always energy, solar energy and the energy from the local grid. When there is no sunshine or at night, the household will always be powered from the energy from the grid. It is cheaper and easier to install than off-grid or hybrid solar systems with batteries. Net metering allows the offset the electricity used from the grid during night or cloudy days. So price-wise, the utility grid can be seen as an energy storage, which is basically cheaper than batteries. It has low maintenance and excess solar energy. So if you produce more energy than you consume, can be exported into the local grid and you can earn money for that. So you're selling your energy. A disadvantage is if your grid goes down, your solar system will shut off and leaving you without power. There's no battery storage or backup applications. So if there is a grid failure, there is no electricity in your house. And you're not completely independent from the grid, so you always need the grid connection. So, are there any questions? So, if you have questions, please collect that and we will give the answers on the live sessions. So, thank you very much for your attention.